Okay, so I think that we are ready to start. So, welcome everyone after 2 weeks break. Yeah, I hope you wasn't missing me. So yeah, so let's see. If nothing strange will happen, I will continue the lectures till the very end of this course. Yeah. As we already discussed, there are no classes next week. Yeah. So I believe that you still have one assignment given from Alexander. Yeah. So today I won't give you any assignment. So then I will have assignment. So because my calendar is pretty empty for the next week. So uh, I will spend it on ranking finally your assignments from those both from both uh, yeah groups. Yeah, because I already signed you two assignments. Yeah. Uh, do you have any questions, by the way? Do I know those? I think that we'll discuss this most likely next week. Yeah, after we will get you will get through in 2 weeks after we will get results. Yeah. So I suppose that you have noticed that I make put incorrect name for the last assignment. Yeah, because I name it after lecture numerical integration, while the actual topic was about programming in MATLAB. But almost nobody complains, so I suppose that it was okay for you. Yeah. I'm surprised how many people submit those assignments. It's a good sign, yeah, because like 3 years ago when I started, I get like mostly six, yeah, 6 to 10, yeah, assignments, and now I get 40. But okay, so it's developing, yeah. And today, this is about the formal matters, yeah. So we are still left with 7 classes, and today we will talk about solving nonlinear equations, yeah. And hopefully we'll finalize this topic, yeah. And thanks to this, we will just end up this preparation for the numerical methods, and we will get more into second topic, yeah. Will it work? Yeah. So yeah, today it's mostly about nonlinear equations. Yeah, there are many methods for solving nonlinear equations. We'll explore today only two of them. Yeah, one is brute force method, as shown here, and we'll show it just to introduce the topic and make some very basic programming, because this method is pretty easy to code, yeah, and understand. So that's why we start with it. The next method is so-called Newton-Raphson method, yeah, and we focus on it because we'll use it in the next stage, yeah. There are many others method like bisection method, for example. Maybe if you take some other courses, you have heard about this. There are also methods that combine, many of them for robustness. Yeah, we'll stick to those two. Yeah, they talk about how to do the stuff, and we'll use Newton-Raphson method quite extensively later on. I put here into italics also the second point about computer-aided analysis of mechanical systems. Yeah, what it means, that means, yeah, that we use computers to analyze some mechanical systems. Uh, most likely we'll just take a very brief glimpse into this topic. Yeah. Uh, and we will start with this topic and continue it through the rest of our classes. Okay. Also here, as you may notice, appeared a second book. Yeah, that it's not very new. Yeah. But well, the topic of this analysis of mechanical systems is also not very new. As most of this is based on Newtonian mechanics, which is also not the area stuff. But yeah, I just put it for reference, yeah, and I do not require you to get this book. I don't know even if it's possible. Maybe you can search on the internet. Maybe it's somewhere openly available. But I will share with you the certain parts of it that will be required along the course. Yeah. Okay. Uh, any questions to schedule? Okay. So let's get to our topic. So solving nonlinear equations. Yeah. So solving nonlinear equations is of course much more difficult than solving linear equations, yeah, because when you want to solve linear equations, you just, we have some specific method that are very efficient and then just provide you this only solution if that exists, if the problem is well defined, yeah. And so, but when you try to solve nonlinear equations, it's more difficult. We just write it in this general form that f of x is just equal to 0. Yeah, and f of x can be any type of the function, yeah. And here you have example, yeah, that if you want to find a solution for this kind of expression, yeah, we just write it as a function by putting everything on the one side to be able to put equal 0 on the other side, yeah, and we just want to solve it. Of course, we are using numerical methods. So once again, we are we are looking for approximate solution. Yeah. So to some with respect to some tolerance. Yeah. That when we hit the point when we are close enough to 0, we assume that we find the correct solution. And there is also issue about how many solutions exist and how many solutions we'll find, yeah, but those are just typical here, yeah. Here in the third line you can see that there is another name for this kind of the problem. This is just root finding, yeah. So those 0 points are called roots, yeah. That's why we are searching for them. And they're important in many areas. Yeah, so those are pretty popular methods. You know, we would like to solve as many linear equations as we can, but our physics is inherently nonlinear. But the main areas are like, for example, here is written implicit ODE solvers. Yeah, have you ever heard about ODE solvers? You were solving PDE, yeah, so partial differential equations using, I suppose, at the end, finite element method, yeah. And but ODEs are just ordinary differential equations, yeah. Do you know what are ordinary differential equations? Equations of motion, for example, are ordinary differential equations, yeah. We'll get back to this, yeah, because when we try to analyze this kind of mechanical systems, as we'll do in the future, we will have to solve also those ODEs, yeah. Uh, Implicit ODEs is just a group of the methods that require solution of the nonlinear equations in each step, yeah. Optimization is another area, yeah, that is now also very common because of the neural network, because then you have to have one of those methods is based on some gradients. So with gradient, you're trying to find the minimum, and in many other areas. And kinematic analysis of mechanism. Yeah, this is maybe not so widespread, but because it's just of direct interest of us, I put it there. Yeah, so we'll learn how to solve those equations, and then we'll apply it to kinematic analysis of some mechanism. But this is a little later. Yeah. So as I described, we start with brute force method. Yeah. Uh, so brute force method, yeah, is has this nice characteristic that it's easy to describe, easy to code, yeah, easy to check, verify, but it's not very efficient. Yeah, but this is often the case with brute force solution. Yeah. So what is idea here? Yeah. So here we have this kind of nice nonlinear function. Yeah. Of course, because we are in this numerical domain, yeah, we will work only with discrete points, yeah. It doesn't matter if this is this fine grid or coarse grid, yeah. We always have just finite number of the points, yeah, here. And let's say that we sample this function at the points that are shown here with those blue dots, yeah. And in brute force method, we will just go from one end, of our arrays of those points to another end of the array, yeah. and we will check if just two points that are next to each other crosses 0. Yeah, and if they crosses it, we will tell that, you know, we find the root, so the 0 point, and then we can calculate where it is. Okay, sounds simple. Okay, yeah, at least to someone. It is simple. It's just, yeah, let's hear. So here it's written in more formalized way. Yeah. So in first point we have a set of points xi, yi. Yeah. And of course xi are some points here. Yeah. Some our discretization. So we have to at least define what is our interval. And then yi are values of our function that we are looking roots for. We have just endpoints typically, and we put those points in the order. Yeah, so this is important for this condition like here. Yeah, so if we have this kind of this set of the points, then we know that a curve crosses x-axis. Yeah, when two points on the y-axis, yeah, like here, has different signs. Make sense? Yeah, I think it's pretty intuitive. Yeah, so we can simply check that if we multiply you know, the y value of one point and another value of the y point, and if we get the value that it's smaller or equal to 0, if we accidentally get into 0, which would be nice but not very likely, but if this condition is met, that it means that we find the root. Yeah, so then we know at least that the root is in this interval from xi to xi plus 1. Make sense? Yeah. So next, now we want to find a better. Okay, now we have to define where is this root. Yeah. So because what is the x for this root? Yeah. We can address this in many ways. Yeah. So we can take either of those points. We could also take the middle point. Yeah. But like here, the proposal is to use just linear interpolation. Yeah, because again, following the rules that we know, that if we make those points close enough, yeah, then it means that if we zoom on the plot between those 2 points, yeah, most likely it will be it most likely will be similar to the line, yeah, following this rule that if we zoom it, you know, properly, and in function behaves appropriately, this will be the case. So that's why we are incorporating this linear interpolation with this equation, yeah, and we assume that this is our solution. Okay, then we can just to be sure we can calculate, for example, f of x, yeah, to check if this is really the case or not. Make sense everything? Any questions? Intuitive? Do you know how to code it? Yeah, how would you code it? Just a rough idea, before we will take a look on the code. Yeah, of course, we need a loop. The basic way that we are solving this type of the task is we need the loop, yeah. So we would create, yeah, the loop among those points, for example, from 1 to n, yeah, because we are working on 2 points. So we have to skip either first element or last element, so we can work from 0 to n minus 1 if we use this kind of numbering, or from 1 to n, yeah, to skip one of them, yeah. And inside we'll check if this is met, this condition is met, and if this condition is met, yeah, inside the loop, then we can calculate the root position x, and then we have to store it somehow. Yeah. Yeah, 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 yeah. Yeah, 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 of course it's possible. You're right. Yeah, yeah, but this is slightly different issue. Of course, it's connected and everything is important, and but then it somehow boils down to the exact problem you are solving, and maybe also to some kind of convergence analysis. Yeah. Those are always hard topics, yeah, because once again, yeah, so you are now discussing about what kind of issues we can encounter when we work with the approximate methods. There are many of them, and but yeah, so and there's no easy way to solve it. But okay, yeah. So let's take a look on the code. Okay, brute force root finder. Yeah. Is it visible to you? Yeah, yeah. Okay. So, of course, the exact implementation depends on the interface that we assume. Yeah. So here, this function is poorly written in the way that it has no header to explain everything to you. So, okay, so I will take the charge. Yeah. But yeah, uh, f, as you can guess, is function. Yeah, because we use this in the code. A, B are points of our interval, like we use earlier, and N is the number of the points. Yeah, and this is reflected here. Yeah. So firstly, because we are provided with the function, yeah, so we generate those points x are arrays x and y, to find the solution inside the function. Yeah. So firstly, we generate x points. Yeah. Next, we generate y points. Yeah. I suppose this is pretty basic. And then we put here an array where we can put insert some roots. Yeah. And next, we run the loop. Yeah. So we, as we discussed, we exclude last point. Yeah, because we are comparing 2 points that are next to each other. So yeah, if we try to get into index I, as we are using I+1, we would get out of the bound. So we have to cut one of the points at one end. Yeah, typically at least I cut them at the end, exactly like here. Yeah, and next is this condition that checks it's if points I and I+1 has different sign, or one of those is already 0. If condition is met, yeah, then we calculate the approximate value of our root, assuming linear approximation, yeah, using this simple equation. Next, we add roots to the array, and yeah, return it to the user. Any surprises? So you can you can tackle this problem in many ways. Yeah, because do you concern about some kind of optimization and efficiency? Because it sounds so. So, or you consider, or you are worried about, if this solution is correct, or both. No, it is correct because take a look. Yeah. Okay. If you are talking about correctness, yeah. So it is correct. Yeah. You can check the equations. We can check it now. Yeah. So if yi is 0, for example, yeah, then this term is 0, and we end up at xi. Yeah. So in the proper place. And if yi plus 1 is 0, then this is 0. This reduces to 1, minus 1. So here you have a plus. So those reduces, and you end up at xi plus 1. No, 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 no. Somehow I pressed something. No, 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 it's not the case. Yeah, so it would be strange a little. Of course, it's possible. Yeah, once again, it's worth testing. Yeah, so if we were to write this function for interpolation, we should write test and check if it is correct at the boundaries. Yeah, as well in the middle. And then it will solve it. It should work for zeros. Yeah, because I cannot see any reasons why it shouldn't work for the zeros, because 0 is just a special case of the points in the middle, yeah? Especially if you have line. Yeah. So yeah, good to test. So we check it. It looks correct. Yeah. So it's fine. So does it address your concerns? Yeah. Uh, because from other reasons I wouldn't split it. Yeah, because we could also split it, because of some kind of efficiency concerns, but I don't think that it is valid. We can discuss this if you want, but simple and shorter code, if you don't need to have it longer and more complex, it's typically better. Yeah. Okay. So yeah. Any other questions, concerns? Fine. Is it fine? Okay, good. Uh, so now let's test it. Yeah. So here we have function demo brute force root finder. Yeah, I think you can guess what is doing. Yeah. Here we have some function that we want to find roots for. We define some points. Yeah, so we want to go from 0 to 4, and we use the grid of 1001 points, for example. Yeah. Then find some roots, and if there are some roots, yeah, we'll tell how many of them they are, and we'll plot them. We'll plot the function, and we will show the roots. Yeah. And if this array is empty, we will just display the message that we were not able to find any roots. Sure. Okay. Questions to this? Let's see how it runs. Yeah. So at least here we can maybe see possibly some of those issues that you have mentioned. Yeah. That uh, we have found quite a few roots. Yeah. So I think that it should even display how many of them we have. So we have like 25 roots, yeah, were found. Because as you can see, what is the function? Yeah, so it's from one, it's cosine of 20x, yeah, but it's decay by exponential function, yeah, so that y is decaying, yeah, to and because of the nature of this exponential function at 4, it's already decay pretty heavily, yeah. Despite that, we are able to find those roots, yeah, most likely they're all of them, because they looks like they are clearly separated. Uh, and if we are to zoom our plot sufficiently strongly, yeah, so like here we have already 10 to minus 7, yeah, we can find, yeah, we can see that, you know, all those roots are valid. Yeah, any questions? Uh, Of course, if we start getting into those smaller and smaller intervals, yeah, most likely we will run into the issues that you have been talking about. Yeah, uh, let's check if it works. Um, uh, if it works for smaller numbers. Yeah, uh, this function looks pretty coarse. Yeah, but still the roots look pretty fine. Yeah, here what saves us, at least partly, is that those roots are quite well behaving. Yeah, because the spacing between the roots is the same. Yeah, and our grid is equally made, and the function is pretty simple. Yeah, so here we can get a good solution even when we use a pretty coarse set of points. Yeah. Um, But yeah, if we were to go with 21, for example, which of course we know already that is too small number because we were able to find with a more finer grid, like 25 points, yeah. And here I will put here locally linspace n times 10. So that why, so in that way, we will show the function in the finer grid, yeah, together with just the roots, yeah. Uh, I suppose that now we will be able to see some strange behavior. Yeah, and it's clearly the case, yeah, that it of course has found some kind of intervals, yeah, like for example, there were here, yeah, that the function, that the sign has changed, yeah, but maybe because it has changed, for example, 2 times, or it doesn't have to even change 2 times, but clearly, yeah, in this kind of long interval, we can see there's this function from here to here. It's not too similar to the line, so that's why, you know, those roots are misplaced. Make sense? Any questions? Yeah. So to answer those issues, yeah, one of the things is just to make this kind of convergence analysis. Yeah, this is one of the basic stuff. I don't know if Alexander has talked about convergence in finite element method, because the idea is the same, like in many stuff. But maybe we already talked about this. This is the same, like also with our numerical integration. Yeah, that if you, for example, use 5 points to calculate those trapezoid and you get some result, yeah, when you use 10 points, you should get the better results, yeah. But when you start adding some points, you will get above some threshold, when this difference will be, you know, smaller and smaller, and you'll stop caring about this, yeah. So you will get to the point that you get all the accuracy that you need, yeah. So in that way, just solving it with more points, because this is pretty important characteristic of many of those approximated methods, that, you know, that when you increase the number of the points, hopefully you will get better solution, yeah. Same applies here. So we could at least, you know, assume that 25 is correct, yeah, because while for 21 points we get just 15 roots, yeah, or if we go to, for example, 51, we already get 25 of them, and they are already correct. Yeah, they are a little misplaced, as you can see, at least as I can see. Let's take a look. Yeah, so they are a little misplaced. Yeah, but it happens. So then we could, for example, check where are our roots, then run it with 101, for example, and then check if the roots are the number of the roots is the same and if they are in the same place. Yeah. So here clearly we can see that they are not in the same place as they were. Yeah. Uh, so this solution looks better. Yeah. And now is the now we can ask to us the question if the previous solution was good enough or not. So then we have to somehow measure it. And if it wasn't good enough, we can, for example, test it with 201 and then compare it with the results of 101. Yeah. And if we are satisfied with those, then we stop going further and we assume that, our solution is correct. So this is more or less, the idea of this convergence analysis. Okay. Any questions? Can we go further? Okay. I don't know if you pay too much attention to the warnings in the MATLAB, but as you can see, this code is almost nice, but it gives us one warning here. I suppose that you cannot read it, yeah. Well, you can increase some fonts, but some of others you can't. Variable appears to change size on every loop iteration. Consider provocating for speed, yeah. Uh, so uh, because this is a very common topic, I thought that we could discuss this a little, yeah. Because do you understand what are the complaints from the MATLAB about this line? Does everybody understand what are the complaints here? Because again, it complains that variable appears to change size on every loop iteration. Does this variable change size on every loop iteration? Yeah, yeah. To be honest, I don't understand why this is problem in MATLAB. Because this is a little strange. Um, because the issue is here, yeah, that, okay, so let's first talk about what is the issue here, yeah, about the pre-allocation. The issue is that as described, we don't really know the number of the roots. Yeah, we know the upper bound, we don't know the lower bound. Yeah, and but still, yeah, we don't know it. So we just allocate here empty matrix. Empty matrix takes just no space, some kind of the pointer. Yeah, but in general it takes no memory. Yeah. So here when you encounter a first root, yeah, uh, you simply execute this command, and as a result, yeah, you will get the array of size 1. Yeah, so you need a space in the memory. Yeah, And as far as I know, if it hasn't changed within the MATLAB in the last years, yeah, the MATLAB will do the following, yeah. So it will figure out, okay, I don't have space there, yeah. So I will allocate memory for this extra element. So like here, I will allocate the space for one element, yeah, put it there, and get rid of this old array, yeah. Okay, this doesn't sound bad, but when we'll go again, yeah, we'll figure out that, okay, I have one element in this root array, but I want to add another one, and I don't have space for it because I haven't allocated this memory, yeah. So he will allocate the space for two elements, copy this one element from the old array, add the new element at the end of the array, and delete the old array, yeah. And it will do this all the times, yeah. So if we were have here some so we will repeat it all the time. So if when we get to 24th element, yeah, we'll have array of 23 with no space for 24th, yes, again, yeah. Allocate memory for 24, copying all those 23 old ones, add the new one, discard the memory for the old one, and keep iterating. It complains here about this, that about the speed for this, because of the simple reason that memory allocations takes a lot of time. Okay, it doesn't take super a lot of time like of our time, yeah, because it takes some kind still like microseconds or milliseconds, yeah. But for the total time of the algorithm, for example, when you make this allocation, the allocation, you could execute some computations like in the like previous line, like for example, thousands of computations for this one memory allocation. Yeah, so this is the issue. Yeah, that in the scale of the computer how fast the computers work and can execute the commands. Yeah, this one takes like for example, 1,000 times slower. So that's why he advises also to pre-allocate. And it's not nice exercise, yeah. Uh, I told that I don't understand why this is the problem in the MATLAB, because the most, for example, solution there are good solutions for that. Yeah, I don't know, like for example in C++. Yeah, in C++ when you have vector, yeah, so vector in C++ always allocate a little more memory. Yeah. So for example, it shows you that you have 4 elements, but it allocates memory for example, for 8 elements. Yeah. So if you add fifth element, it does nothing. When you allocate sixth element, it does nothing. When that allocates seventh element, still nothing. Yeah. And when you try to add, for example, ninth element, then he will make this procedure. Yeah. And of course, the goal here is to make it, as few times as possible. Uh, so okay. So that's why, there is the question, can we avoid this? Yeah, this is some kind of exercise, because in this kind of example, it doesn't really matter, yeah? But we would like to see what is the impact of it. And firstly, and second, uh, how to solve this issue. An idea how to solve this issue? How we can pre-allocate this array without knowing how many elements we will get. Yeah, yeah, yeah. It's in general, it's a good idea. It has one drawback, though, that it's just can be memory heavy. Yeah, so here once again, yeah, we have mostly those toy examples. Yeah, so it's not a big issue, because if we have array like 1,000 or 10,000, yeah, it's not really a problem. It would be more problematic if we start to have arrays of 10,000s. But as general solution, because we don't know what user will do, typically it's not the best one, the best solution. Yeah, because we can end up that we allocate those 1,000 or 10,000 or even million elements, and still we'll have a single root. Yeah. So of course this is yeah, very good idea, but yeah, yeah. We can there are better solutions in that way. Yeah. So we can do better. Any ideas? Because I already told you how to do it. Just 3 minutes ago. You allocate a little more that you need, you fill it in, and when you hit the boundary, you allocate even more. Yeah. So that's why in that way, yeah, you do not pre-allocate. So then, because it's to get some kind of balance, yeah, between the memory needs for our program and computational needs for our program. Yeah. Sometimes in time critical applications, you really have to take a look on it. Here with MATLAB, we typically don't, but it's good to be aware of it. Okay, so here is the example, yeah, and you can already see one reason why not to do this, yeah. So I have done it, yeah, and why? So why not to do this? Because it starts to get pretty long, yeah, and you have to take care about more things, yeah. So so is it a good idea to do this per allocation or not? Because as you can see, this code start to be far more complicated. Yeah, here we solve everything in like 12 lines. Yeah, and here we solve exactly the same task. Yeah, but we use like 20 lines. Is it worth the effort? What can be answer to this kind of question? Always the same. It depends. So where should we when should we take this effort? No, okay. It's more about general idea. Yeah, yeah. So the idea, because now we try to optimize it for speed. Yeah, and Mimi, and also because we haven't used your simplified approach, we also optimize it somehow to memory. Yeah. So we try to find some balance between the memory and the speed. This is very general consideration, and it appears many times in numerical analysis. And the answer, and in general in coding and in programming, and the answer to this is that you should do this when you see that this is needed. Yeah. So it should start with benchmarking. Yeah. So we won't get into benchmarking. Do you know what is benchmarking? Benchmarking is it's about measurement how your code behaves. Yeah. So it's about measurement efficiency of your code. Yeah. So normally we should benchmark our program because this code is used in wider context, yeah. And we figure out that our, for example, simulation runs for 3 days, yeah, and we are not super happy with it because we are expecting it to run in 1 hour. We could start, investigate, benchmark it, and if we find that this function is slow, yeah, then we will re-implement it for better efficiency. Yeah. So correctness goes first, and then goes benchmarking if you have to optimize for memory consumption or for the speed. And this benchmarking step is very important because sometimes it's really misleading about, if something will help or not. Make sense? Okay. So, but let's get to more concrete stuff, how it's done here, yeah? So, start is the same, yeah? So for the start, we just generate those numbers. Next one, we start to introduce some magic number like here. So we start magic number 10, and this magic number tell us how many elements we can store in our roots array. Okay, so that's why we put here some zeros, R max 1. Yeah. Next, we have to store, because we cannot edit at the end, yeah, the new roots, yeah. So here we are storing the information how many roots already are stored in our array. Okay, so it tells that we have 0 roots. So now, then the next few lines are the same, yeah. So iterate, check condition, calculate where is the root, and here is this the most complicated part, yeah, when we insert the new root, yeah. And because we are working with this kind of pre-allocated array, and we are not sure if everything can fit inside, we have to do the following. So firstly, we update the index of our current root. So now we add 1 here, because for the first root we want to put it on the first position, yeah, and so on. So next we have to check if we have space to put those roots, yeah. So it's done in the way that if we want to put the root outside of the array, we will allocate more memory, yeah, and it's done here. So we are just extending roots by its length, yeah. So we will be doubling the length of the roots, and then we have to update Rmax, yeah, for that. And after all that, we are sure that we can safely put the root into the array. So we just put it. And at the end, so it continues that way, yeah. So it will just allocate the memory just few times, yeah, for sure, fewer times that at start. At the end, because we are not interested into passing all those zeros, we just return the array from index 1 to how many roots we already have in the array. Make sense? Does it look like it could work? Yeah. uh, so it's here, yeah. And now we can check with function time it, yeah, if it was at all worth doing, yeah. Time it is function just to make this kind of short benchmarking, yeah. You can check it here, like typically in documentation. If you know Python, you can figure out that in Python there is also time it function, and I suppose that the name came from there. Measure time required to run function, simply like that. The issue is that it's not so easy to measure time required to run function. Yeah, that's why there are special functions for it. But it's like with many stuff, it's a slightly longer topic. Yeah, so there are really many details into it. So we'll try to try to time it those functions. Yeah, so we have it here. Yeah, so what do we have here? Yeah. So if you want to time it, we need a problem definition, yeah. And then we want to time those two versions and compare them. As you can see here, firstly, I use TikTok to do the same, yeah. It's easier, but time it is just more correct way of doing stuff like that, yeah, because you can read in the documentation why this is the case, yeah. But because we have already something that is designed for this purpose, we'll just use it. Okay. So as always, yeah, we check what is the header, yeah, and calls f with the desired number of outputs. num outputs. By default, timeit calls the function f with one output or no output if the function does not return any output. So we have function with one output, so we can use the default version. So measure the time in seconds required to run a function specified by the function handle f. Pretty easy, yeah. Mm. So in order to run it, yeah, we want to run firstly this function, yeah, and because we need a function handle to run this function, so what do we do? Do you remember? How to get handle for this? Yeah, 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 but we cannot put at here and run it that way because then we would create a handle for this specific function, yeah. But the issue is that I'm pretty sure that it won't pass those arguments because how to pass those arguments, yeah, and our function won't work without those arguments, yeah. So we have to create anonymous function, yeah. We will create anonymous function, and then anonymous function will look like that, yeah. So this is just the standard way, by the way, how to pass some extra arguments to MATLAB code, yeah. And then we can create anonymous function for our second. And then we can time it. Okay, here, yeah. So it will return the time. So T1 is equal to time it for brute force should be RF. Brute force root finder. And let's run it and see the results. It should take a few seconds. Okay. So we can see a few things here, yeah. So first of all, it works, so it's nice, and then you can see that this number, those numbers are pretty close to each other, yeah. So it can indicate that it's not really worth doing the work, yeah. And it could be true because I have this course like already just a few years, yeah. I started with some doctoral course like 5 years ago. So why I mentioned this? Because those numbers were totally different in those days. So and why? Because of MATLAB, yeah. Because MATLAB, I think that it seems that they are starting addressing this issue as well. So maybe they also changed the policy because in the old days those numbers would be totally different. Yeah, that this number could be like simply 10 times larger than the second one. Yeah. So now it is closed. So I mean, even wonder why they still bothering with putting this input there. That you can consider it pre-allocating because now it's just simply misleading. Yeah. So we take a lot of time to optimize it. Yeah, and still we get just very minor improvement for it. Let's see if this is still the case for something more challenging, because if we put here simply cosine, yeah, it will oscillate more and more. So if we just increase the size of the problem, yeah, so if we increase If we increase simply the point here from 4 to 40, it means that we will have 10 times more of the roots, yeah? And here we also increase the number of the points. So here, instead of 25 roots, we should get something like 250. So we'll get far more prior allocations in the basic version. So let's see if it scales well. And as you can see, it scales really well, yeah? Okay. It runs too fast, yeah? Something is, I'm not very happy with those results. Simply because, it shouldn't happen, all that, yeah? So first, yeah. But let's not complain about the MATLAB. But here we can see that we get 10 times faster code. Yeah, for example, if we increase just the size of the problem. Yeah. Okay, conclusions. Yeah. It seems that in MATLAB, I stated prematurely. Yeah, when we just increase the size of the problem, we can see that still prior allocation is a big problem in MATLAB. Yeah, we get 10 times faster code. Yeah, like here. Yeah, just by adding those 10 lines. Uh, is it worth doing to get 10 times faster code? Again, it depends because of the reasons we discussed earlier. Yeah, if we figure out that this is bottleneck and it's worth speeding up our program, we should do this. Yeah, if we have resources. If not, then just leave it and just ensure that it works. But okay, any questions? So let's go to more to nicer topics. Yeah. So now we were discussing mostly about programming issues, programming principles, and how to tackle some uh, just issues connected with efficiency and memory consumption. Now gets back to algorithmic side. Yeah. Newton-Raphson's method. Do you know Newton-Raphson's method? Have you ever heard about this? Okay, some of you has, some of you doesn't. Uh, as you can guess, because of what we are talking here about, it's another root finding method. Yeah. As it's written, it's widely used in practice, and one of the reason is because it's simply fast. Uh, it has some drawbacks. Yeah. So we can already talk about this. Like one is written here that it doesn't guarantee to find the solution because it can, it's iterative method. It can diverge. It's also meant to find one solution. Yeah. But when properly used, it gives you the solution that you are looking for, and it gives you fast. Yeah. That's why it's commonly used. Yeah. And the idea is put it here. Yeah. So we have this kind of nonlinear function, but computers typically know how to solve linear functions. Yeah. So so following those two information, we will start with some point, linearize function here, solve this linear function, yeah, and hope that doing this multiple times will bring us closer to the solution. I will show the scheme on the next slide, yeah. We'll test it on this simple function. Again, we change the function because this method just finds one root, yeah. Uh, so I can maybe show you the code and then we'll check how it works. So it starts with naive Newton, yeah, and why it's called naive simply because this is the most basic implementation. As you can see, it's even shorter than brute force. Yeah, we're able to write it in 8 lines. Yeah, if we exclude and, it's just like and we exclude that because it's not truly needed. Yeah, so it's like 2 lines of code. So here you can see that it takes slightly different set of arguments that our brute force method. So it takes, of course, our function, but as you can see here, it takes also derivative of our function. because what is derivative? It's of course linear's version of our function, yeah? And by having this linear version of our function, we know how to solve linear equations. So we'll use this this fact that it gets starting value, yeah? So previous method gets interval, yeah, and find solution in this interval exclusively. Here the principle is different, yeah. So you give it starting value, so some starting point, yeah, and you are trying, yeah, just to find the solution that is hopefully close to the starting point. So it works when you know more or less where is your root, yeah, but you are not so sure, yeah. And some kind of tolerance, because you need, yeah, here the method is iterative, yeah, so we need a tolerance to stop searching for the root, yeah. Uh, and it works that way, yeah, that we start with our starting value as our x. Then we are checking that maybe this is already a solution, yeah. If it's and we check it by evaluating y, so value of the function. So simply, if the value of the function is larger than tolerance, it will run the next iteration in hope to find a better solution, yeah. And it will of course stop when it will be close enough. And here is the actual evaluation that hopefully will bring us to the closer solution. Yeah, so this simple equation, we'll see it in a second. And that's all. Yeah. Uh, so firstly, we can see how it works. Yeah. So we provide it with the solution. Yeah. Because the method requires also derivative, we just calculated. Here, fortunately, it's trivial. We run 9 Newton. We start at point 1000 and require tolerance 10 to minus 12 to get close to 0. And then we will display solutions. Yeah. So 1000 is quite far from the actual solution because you can calculate it pretty easy what it is. Yeah. But let's see how long it will take this method to get from 1000 to this 3. And as you may remember, it has 2 solutions, and of course, because of characteristic of this method, we will be able to find only one. Yeah. So get very close to the exact solution, yeah. And as you can see, that doesn't take even so many steps, yeah. Despite that, we were very far from it, yeah. So if you were to use this kind of brute force method to find this point, possibly with good accuracy, we really need to use pretty large number of the points. And here we can see that more or less the method halves the distance between the solution and our solution that we are guessing, okay? Because we start with 1000 and then it goes directly to 500, 250, 125, and so and so. And just after a bunch of iterations, like maybe 10 of them, yeah, we get the correct solution. So it's really fast, so you have to calculate the small equation just like 10 times, and that's all, yeah? So here algorithm is shown in more detail, yeah, so you can see that it works, yeah, you know already its main characteristic. So again, it works in that way that here, for example, we start, yeah, so this is actual this x squared minus 9, yeah. So we start here and we are linearizing this function at that point, yeah, that's why we need this derivative, yeah. So here we have this derivative. And with why we have derivative, it's very easy to calculate because it's just simple line. Yeah, it's very easy to calculate where is the next point, like x1. Yeah, and here is equation. Yeah, so we just have the old point minus just value of the function over the value of its derivative. Yeah, because value of the function is this point, value of the derivative is that point. Then we get this distance. Yeah, here it's even written, what is the equation for this tangent line. And based on the equation of the tangent line, we get this iterative process. So we get the next point, and again, yeah, we check that at this point, this function is far from zero, so we repeat it, yeah. Find this point, get tangent, find the next point. Far from zero, repeat, and so on and so on. Any questions? Is it clear how it works?
For example, if I choose, I can find only one.
Yeah. If you have 1,000, you can find only one. If you have 1,000, you can find only one. Yeah, it only gives you one. One call to this function only gives you one. Yeah, yeah, yeah. Of course, your concerns are very valid, and that's why when you want to solve some problem, like for example, if you want to find nonlinear solution of the nonlinear function, you have a lot of methods to choose from. Yeah, and all those methods have some kind of characteristic that depends of how they work, how about efficiency and robustness. Yeah, and it's just proven that this method works well in certain scenarios that we'll use it. That's why we use it. Yeah. Um, so there are two sides of the story. So you always have to, choose the algorithm that is correct for your work. Yeah. And sometimes, of course, this is hard. Yeah. Especially if you start. So that's why Newton, this kind of method is not very good. If you need very robust method that finds multiple roots. Yeah. That then you have to use another method. Does it help?
If I choose the starting point, it's a guess correctly, I can find all the roots.
Yeah, possibly. But yeah, or no. I'm not sure if you can really find all the roots in all cases with this method because it has some extra convergence issues. Yeah, that we'll discuss. But in general, this is the case. Yeah. But so it brings us also to the combination of the method. Yeah. For example, we can combine, so for example, some brute force search or different type of the search with this method. Yeah. That, for example, but it's something difficult, yeah, that you can use different method to get close to the zero, but with some method that is more costly, yeah. And then when you get close to zero, you can, for example, run a few iterations of Newton-Raphson to get very exact to the solution, yeah, to make it more argumenting plausible, yeah. And addressing your issues, there is modified version of this method. I think it's called second method, if I'm not mistaken, yeah. And it works in a way that instead of using derivatives, so instead of using tangent line, it can use this second line. So if you can get point here and just put line through it. Oh, and um, so then it will work in similar way. It it proves that it convergence is reasonably slower, yeah, but then it can work on a bunch of points, possibly. Or in the case when it's just hard to get derivative. So again, we know how to use this method. We know that it will find one root, it requires function, its derivative and starting point. And if we have applications that can gives us those in a reasonable way, then we can use it because it's fast. Yeah. If not, maybe we should find for something that is more robust, adaptive and so. Yeah, but it's typical, yeah. Like for example, we discuss about those ODEs, yeah. If you will type ODE in help for MATLAB, you will find like 10 methods that can solve ODE. Which one to use? Depends on the case, yeah. There are some guidelines, yeah. Start with OD 45. If it's slow, go there. If it's inaccurate, go there, yeah. And so and so. So you have to combine algorithm to your problem. in proper way. So numerics is complicated, and that's why I don't know if you've ever seen the books about numerical methods. Yeah, have you ever seen? So like the classical books on numerical methods are like that wide, yeah, and they are written in very thin paper, so they are easily like 1,000 pages, and with small font. And you can find just like for example 20 methods for solving nonlinear equations and many 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 other things. So we are just scratching the surface. But okay, yeah, you always have to start somewhere. Uh, so here is this algorithm put into more formal way. So by using this approximation, yeah, by using derivative, here we have this iterative scheme. And here this condition, yeah, under which we are satisfied with our solution. So once again, approximation numerics, we need some kind of tolerance that is good for us. Here we choose it to be constant 10 to minus 12. All the things that we discussed about, tolerances last time applies here because this function is the range of 1, 10 to minus 12 is sounds like good number. We already have seen implementation, and you can see that we don't need any array for xn, by the way. I don't, so it's also very memory efficient, as you can see, because there is no reason to store all the history until we really wanted to, because we have some specific reason for it. Yeah, so it works only on scalar x. And okay, yeah. Questions? So here is about another characteristic of this method. Yeah. So here we can see this function that doesn't look so looks quite okay, is hyperbolic tangent. Yeah. So when you plot it, it looks like that, and it has well-defined derivative like here. Yeah. And here is a task to run this Newton-Raphson, yeah, with those two initial conditions, 1.08 and 1.09, yeah. And of course, the goal is to find a root that is at 0, yeah. So here you can see already that the code is written, yeah. So we have function, we have derivative of this function. We can check they are correct. And now we are looking for root, yeah. And it starts in firstly ask us to find it from the point yeah, starting value 1.08, yeah, and tolerance 10 to minus 6, why not? Yeah, so not so long, not so small, pretty fine. And if you run it, we can see that after 1, 2, 3, 4, 5, 6, 7, yeah, like 7 steps, and we are end up really close to 0. Yeah, so in machine precision it's just 0. Yeah, 10 to minus 15. So it's a very satisfying result. So what will happen if you go to 1.09? Again, about the rules of the examples. What will happen? Most likely, what is the outcome that you are expecting?
Maybe is the value like in line,
Hmm.
derivative is
Yeah. At least your retention is correct. Yeah, so it will fail. Yeah, and it will fail pretty quickly. We can see it here. It just stops because it gets to not a number. Yeah, so we just get out of the bound of any numerics. Yeah, and as you can see, it stops also pretty quickly. But simply when we start from 109, it gets to larger, and larger values until it gets to some super large and then totally infinite overflow. And when we operate on infinites, we get not a number very quickly. Yeah. Uh, if it weren't about not a number, we will just get some crappy results, strange results, or whatever, yeah, it fails. And it diverges exactly because of the reason that you described, more or less, yeah, that because of the how it's shaped, yeah. When we start when we start here, it gets a little closer, but when we start just a little further away, it gets a little further, yeah. And when it gets already a little further, then it will go further and further away, yeah. So here I have much longer version of this, not super long at least, yeah, but a little longer, and it plots simply the steps of the execution, yeah. So if we go with 108, okay, yeah, we have to run this in debug mode, yeah, to make it run properly, yeah. So let's run it in debug mode, okay. What is the step here? Okay. So we can put it here, yeah. And okay, now I think it will be a slightly better, yeah. So here we have the code, yeah, and here we have we will see how the plot will be generated and how the those tangent lines will be plotted in the next point, yeah. So now we have just plotted our function, yeah, and we have plotted just zero line, yeah, so for the reference. And here we have in general, as you can see, loop of this Newton-Raphson iterations, yeah. But along it we will plot a line, yeah. So we started at 1.08, yeah, and this is the first tangent, yeah, and you can see that 0 gets here, yeah. So it's even hard to tell if it's better or worse, yeah, but you can see that it's even hard to see. But we'll display X here, yeah, so soon we will see if it's better or not. So it's minus 1.059, yeah, so it gets closer to our root, yeah, so this is a good sign. So if you plot the next line, and you can see that already here that this is boundary case, yeah, because I don't know how about you, but you know, it's hard to tell. Those lines almost looks like they are parallel, yeah, those tangents. So this is the root of the issue, yeah, that because they are parallel, they can either get a little closer soon or a little further away, yeah. So here we know that it solves, yeah, so it gets closer. Now you can see that the new line is visibly closer. So next, then it will converge pretty quickly. Yeah, so yeah, it's getting better and better. Yeah, so here's the next line, and here's the root. And the new line already end up very closely to 0. Yeah, so I will just let it run because it just, okay, so it just makes one more line that gets close to 0. Yeah, because here we put pretty rough tolerance. Yeah. So by the way, this is the way how it works. Yeah, a nice thing. And again, if we use 1.09 as an example, beginning is very similar. However, you can already see here that those points start to be get further and further away. Yeah, here is by just by a very small margin, but it's get further away. Yeah, so those lines, again, at this stage are pretty parallel, still pretty parallel, but you can already see that they start diverging. Yeah, new line gets further away, further away, further away, and that one, that one is almost horizontal. Yeah, so no hope. Yeah, we will soon get some. Yeah, and as you can see, the coefficient here is just totally ridiculous for our scale. um, Infinite, not a number, and end of the program. Yeah. So this is how it happens. Yeah, it happens, slowly getting, further and further away until it's totally collapse. What we can do about this? Yeah. So first of all, we should make our code more robust. Yeah, so this is the technical stuff that we should do because we should predict it, or we should, because either we get results that doesn't make sense, and we should report it somehow, like not a number, or we could get into infinite loop because here on this tangent, it's pretty simple to say it, yeah, because it's clear example, yeah, is this benchmark. But they can be like more sophisticated, issues, yeah, that will be some kind more oscillatory, and we can end up with like, just infinite loop. Yeah, so we also do not like infinite loop because they takes quite a long time and consume a lot of resources. So we would like to firstly write our function in the way that handles this kind of the issues. Yeah, this is pretty easy, yeah? And it's also one of the way how you should write the numerical methods that can be reused for others in a better way. So this is one thing. Another thing is, as you tell, yeah, in practical applications, we have to ensure that our initial guess is pretty close to actual solution that we're looking for. Yeah. So another hint, we can use Newton-Raphson method mostly in the ways that are either very well defined, because whatever you will do with this parabola, it always has correct shape and it always gets to the correct solution. So for parabola type functions, no issues at all. Yeah. Or just have examples that do not maybe have this kind of guarantees that they are convex, yeah, but that the function that the initial guess can be found close enough in the way that we will find the solution. Okay, so by the way, here how to robustify it, because we know that it can diverge and run forever or just return some ridiculous values that are not very useful. Firstly, we should limit the number of evaluations just to be sure that it won't get into infinity. Sorry. Then we should limit the number of evaluations. Okay, no, we already tell this. Next, we should check if just those numbers are finite, if we just get, still the numbers, yeah, because we can discover if we get infinite values or not a number. Um, by the way, we could call this function only once, yeah. Here, if we take a look on the code, yeah, of our, let's get back with editor in the old place, yeah. If we see Newton-Raphson, you can see that we call function f of x twice. Yeah, this is very small. This could be minor issue or might not be minor issue. It's very easy to call it once. On the other hand, it can be really waste of time to call it many times. Yeah, because here it evaluates fast. Again, it's not an issue, but um, it can be the case that this function takes pretty long time to evaluate. Yeah, so this is very small implementation detail, but it's just worth taking care of. Yeah. So to address those three issues, here we have Newton method. we call it Newton. It has the same header, the same input to the function. Well, this is the same method, yeah. So that's why it takes our function derivative, initial guess, and tolerance. I will change it maybe to tolerance. We know that APS is special function, so let's get it. It's significantly longer, yeah. It's still pretty simple, yeah, but it's much longer, and it's much longer because of those considerations that we wanted to address. Check for the values, limit the number of iterations, and ensure that the function is called just once, yeah. So and here's one of the solution, yeah. So first line is the same. We start with initial value because we want to evaluate function only once for given x. So that's why we evaluate it here and use it twice here. If we want to limit the number of iterations, we need some kind of iteration counter, yeah. And also we need the set maximum number of iterations here is set to 100, yeah. So our while gets a little bit more complicated. So firstly, we have the same condition like previously, and iteration counter less than 100. Yeah, 100 is plenty for Newton method, yeah. Then is actual Newton-Raphson step. Then we check if value is number. If value is not a number, or if value is infinite, then we'll put here information about the error. Maybe not the best solution, but it worked for us, yeah. So we manifest somehow the error and break execution. If not, again, get function value and iterate. Increase the iteration counter because we have to increase this counter because if we to limit the number of possible evaluations. So yeah, here is the simple check because now as you can see we are returning two values. Yeah, so first we return solution and a second parameter we return the number of iterations. Simply, if the function value is not within tolerance, we set the iteration counter to -1. So if iteration counter is -1, it means that it fails. Solution equal to x and number of iterations is iteration counter if everything is correct. Yeah. So this, yeah, just like that. Any questions to this code? Can you say that as compared with this naive Newton, that would much nicer and shorter. We still have those common points. Let's unify the naming. Yeah. Still have all those same lines like here, starting value, here while loop, here is Newton iteration, and returning of the results. We add all those lines to address those three concerns. Yeah. Yeah. That break. Uh, Normally, okay. So breaks. I don't remember which one. Yeah, but in general, breaks the loop, stops the loop. Yeah. So simply, uh, this part of the code means if we have this kind of values that are not real values, yeah, and we cannot operate further on them, there is no need to make any more iterations. So just break the loop. The while loop, yeah, yeah, because there is one loop here. If it's just a condition, yeah, it's almost always done in some if, yeah, that if some values then break, yeah, and this break relates to the loop. But if it's not a loop, yeah, if you point out, yeah, because if it's just condition, yeah, so it's not iterative, yeah, so it break loops, yeah. So if we have for loop, we can, if we put break, it would break it as the same, yeah, break the iteration and goes after for loop, so it works for loops, yeah. And then, of course, because we are already inside this loop, we know that this condition is not met. So this condition also won't be met. So we will get this this -1 as and it will show that for the code that we can check that there is some error there. Okay. So well, yeah, unfortunately, you can see also this effect that why writing the first version of the algorithm that just works is can be often pretty easy like that. But if you want to make it robust and to provide it for someone else to use in a way that you get confidence, that even if you try to misuse it, it will still, give you something useful like error, yeah, that something is wrong. It takes quite a bit. And it's not even full because we should even check if the input arguments are correct and so and so. So it's really, this is one of the reasons why writing production ready code, yeah, in huge groups, it's quite challenging, and it's, you can see easy how easy it's to make any kind of errors. Okay, makes sense. Okay, so we still have some time. Good. So let's take a look how it works. We have demo here. Okay, so we have demo here, so it's a good sign. uh, so we have demo for the Newton's method, yeah. So firstly, we can run it with our with the same example, x square minus 9. Almost all the same. We can even put here 12, it doesn't really matter. And if you run it with just this kind of message, yeah. Number of function calls 14, because now iteration counter is also number of function calls. And solution is 3, as we expect, yeah. No. Okay. So if we change to this example of hyperbolic tangent, as we get 1.08, it should work the same. So let's run it. Yeah. Okay. Solution -0, but it doesn't really matter. Yeah. Close to 0. If you would round it, it would be 0. And if we put that one, yeah, we get as expected error. Yeah. So that x is gets some infinite. Okay. Yeah, because it gets infinite, and because we check if number of iterations is larger than 0, we get -1 as expected. So we know that the execution of the code was aborted. Much nicer than some kind of debug all that stuff, yeah. And the nice thing here that you can check it in your code, yeah, and if the code depends on it, you can take some actions. Questions? Can we go further? Nice. So another topic, derivatives. Yeah. So just a hint, sometimes that you can combine what you know. Yeah. Even if you don't know derivative because it's complicated, you can use what we have discussed about symbolic computations to calculate the derivative. and they are pretty good on this. Yeah, there are many ways to get derivative. There are numerical methods, that are automatic differentiation method, and there are those symbolic computations. Yeah, like here. So because we already discussed about symbolic computations, yeah, so you know what it is, yeah, and here's an example of how this can be simply done, yeah. So if you really, so you can use it if you really want to get derivative because you want to use Newton's method, but it's too time consuming to calculate it. Yeah, or for example, you want to test something and don't want to bother really in calculating it. Yeah, whatever is the reason. And procedure is pretty easy, yeah. So of course we have to tell the MATLAB that now we are working with symbolic toolbox, so SimsX to get symbolic calculations. Then we run the expressions for our function. Like here we use the same simple expression. Um, I think that this command should go here. Something has happened here. So some errors with the code, yeah, because here should be the line that calculates this. So I don't know what happens with this code, line of the code, but we can simply fix it. So we want to get df dx, and we want to differentiate our f expression with respect to x. I don't think that we even have to provide this information. Okay, those warnings are typically useful. Okay, so let's check it. Just let's check it. So f expression is as expected, and what is derivative? It's also as expected, so it works. Yeah. Uh, but this is not very useful because it's still a symbolic expression, yeah. So we would like to have function, yeah, because what we expect to provide for this Newton-Raphson is preferably MATLAB functions, yeah. Functions runs much faster than this kind of expressions, yeah. But here is written the way how to generate simple MATLAB functions based on symbolic expressions, and it's called MATLAB function. Yeah, so not very nothing super sophisticated. Simply f gives you a function handle of this type. So function handle is a function, just save as variable. Same here. Yeah, so it's function. So if you call it like that, it works. It prints value. It behaves like a function, and you can already use this and pass it to Newton-Raphson. Yeah, so we can now run Newton method with our f and df dx that we just get, yeah, and we just provide some this initial value like 1001 and minus 14, and it gives us the answer. Yeah, so works simply like that. Here is the code snippet. If you want to save this code you generate into file, because this is more typical, yeah, to make it more just persistent, yeah. So here you just get something variable that sits into memory. So simply if you call the same MATLAB function for your expression and you just write that you want to get file, and here is the file name, then it will just generate a file name. Yeah. So if we run this, it gives you function handle again, but now it's function handle to something that it's on the disk. Yeah, and you can see new created file, some header. This function was generated by symbolic math toolbox. Here is just expression because it's super simple function, and that's all. Works nicely if this is not some extremely complicated. So I think it's just good to know. Questions? Okay, so something that is now super interesting and important for us. Solving multiple nonlinear algebraic equations at once, yeah? So this is also why one of the reasons why we want to use Newton-Raphson, yeah? Because it's based on those concepts like that we have tangent, yeah, that we have nonlinear function, that we solve this using linear equations. You can easily abstract it out to multiple equations, yeah, because then we have this kind of function in multidimensional space, and instead of a tangent line, you have tangent hyperplane. But even if it's hyperplane, it's still linear, yeah. So we can find it and solve it for all those zeros, yeah. Why it's important? Because in many of those applications, if you have either those ODEs or our kinematic examples, often you have more than one variable that you want to solve and more than one equations that it's non-linear. We will quickly see it, yeah? So it's common case. And in that case, we can use it, yeah? So first of all, here is just problem definition, yeah? Uh, so this method, we want to solve many equations. So we have n equations, f1 to fn, and those n equations have full rank. So it means here in the practice that the problem is well defined when the number of those functions is equal to the number of our unknowns. Yeah. So we have two functions we can solve for two unknowns. Uh, then Newton-Raphson is suitable, yeah? And we want all those functions to be equal to 0, and we want to find all those variables fx1 to xn that will just meet this requirement that all those functions equal to 0, yeah? Of course, we assume that the problem is well defined, so it means that the solution exists, because it's very easy to write it that it doesn't exist, yeah? But yeah. Is it clear what is the problem? Yeah. So we don't want to write, of course, all those things all the time, that f1, fn, and so, yeah? So introduce vector notation. Are you familiar with vector notation? Okay, perfect, yeah. So we introduce vector rotation in the way that f bolded, yeah, in lowercase f bolded is a vector. We will write vectors in columns. That's why you have transposition here. So it's simply a vector of all those functions. And analogically, x, lowercase bolded, is vector, column vector, of all our unknowns. Yeah. So here is an extract from nomenclature for matrix calculus. Yeah. So matrices. So it means that entities, we will just use these terms vector if it's just one column, or matrix if it's just multiple columns typically. Matrix boldface uppercase letters. Okay. A, J. Column vectors, matrices, and algebraic vectors are boldface lowercase letters like this X, B, and F. Scalars, as usual, lightface letters. Yeah, so scalars, business like always. AT is row vector array because of this transposition. Normally we use column vector, so of course transposition puts it into row, which is nice for showing it on the slides typically. This kind of bolded O, 0 is zero matrix. What is zero matrix? Yeah, it has only zeros, yeah. And capital I bolded is identity matrix. Do you remember what is identity matrix? Exactly. And if you can multiply for identity matrix, and then if you can multiply, then you get the same matrix. So it's no neutral element for matrix multiplication. Okay, so then using this nomenclature, we can write the previous equation in this form. That's simply f, and f, as we remember, has n functions, yeah, and x has x variables. So we can replace it by this expression, that f of x is equal to 0. Yeah. So as you can see here, it looks almost the same like scalar case. Yeah, just we make it bolded, so we make it in multi-dimensional instead of scalar ones, but expression is exactly the same. Here I believe it's nice to have specific example. Yeah. So let's say that we have two variables, x and y, yeah, light phases, and we have those two functions. Yeah. So like here, and we want to solve them, those two equations, two nonlinear equations for x and y. Yeah, just solve them. Yeah. So if we want to use this description, so firstly we can write that x is simply contains xy as variables. Make sense? Yeah. And f of x is function, vector function with two entries because we have two equations. And one entry is just first equation equals to 0, so we have to put all the terms on one side. Yeah, so we put all the terms on one side and write them here. Yeah, and we do the same for the second equation. We put all the terms at one side. It doesn't matter which one because we compare it with 0. Yeah, yeah, and make it here, and we want them to be 0. Everything clear? Perfect. So now, so how to tackle it? Yeah. So we could, of course, make it easy, this geometrical interpretation of Newton methods. Yeah, so we could make the tangent, calculate angle and whatever, and write those equations. Yeah. So of course, there are extensions in math to tangents in the context of nonlinear equations, and it goes through Taylor expansion. Have you ever heard about Taylor expansion? Yeah. So, as you may know, Taylor expansion is the way how to express. You can express function at given time and given point, yeah, as so. In Taylor expansion, function of x at certain point can be expressed as the same function as different point plus derivative of this function, first, second, third, and to infinity if they exist, times this kind of differences between those 2 points. Okay, this is more or less how Taylor expansion works, yeah. And it is useful because you can cut those higher terms numbers because they contribute less and less towards the change in value of the function, yeah. Here we just save first derivative. We'll explain in detail what it is. So we just save the first derivative. But we do the same in Newton function for the scalar. We just use single tangent, yeah? So here we use also this single tangent hyperplane, okay? So of course, as you can see, it's approximated solution, yeah? But we know this already. This is exactly the same analogy that it goes to Newton method. It was also approximated. And then by using this expression, and running it into the loop, yeah, we expect to get correct solution. And all those considerations that we have with Newton methods applies, yeah. So it will find only one solution. It can diverge. So we should ensure that this point x is still close to the solution, and when it close, it and it and if it can converge, it will converge very quickly to actual solution. Yeah. So yeah, but what is this one? Do you know what is that one? What is this term? No, it's only first order. It's gradient. It's gradient of our function. It's only first order derivative. So we remove all the higher order terms. Yeah. If you want to have second order derivatives, normally you would put number 2 here somewhere. So it's only first order derivatives. Yeah. Yeah, exactly. So it's shown here. Yeah. So this delta f, I think is gradient f, is, if you write it, is just partial f partial x. Yeah. So first order derivative of our function with respect to its arguments, yeah, is the matrix of all partial derivatives of f. It's matrix because, and it's square matrix in our case, because if you want to calculate all those derivatives, yeah, we have n functions, n functions and n variables. So we have to calculate all those df1 over dx1, df1, dx2, and so. But also we have to go into the second direction, so df2 over dx1, dx2, up to dxn, and so and so. Yeah? And after calculating all this, we have this kind of the square matrix. It's called typically J, capital J, because it's Jacobian matrix. Yeah, so this is Jacobian matrix, grad f, or partial derivative of f with respect to x. And to preserve the consistency, it's calculated in the way that the first row contains derivatives of the first function with respect to all the variables. Second row, its second function with respect to all the variables, up to nth row, which contains all the derivatives of the last function fn with respect to all the variables. Is it clear? Understandable? Yeah. So this is how this is defined. So now, do you want to calculate this by hand, by me, just to show that it works, or because, or this is simple enough? Yeah. Okay. Good. So we get to this example. So in our example, we have two variables x, y, yeah, and function that contains with two rows, function 1, function 2, yeah. So our Jacobian matrix, yeah, which is this gradient, is of course derivative of function 1 with respect to x, derivative of function 1 with respect to y. So this is the first row. First row contains, once again, first function with respect to all the variables. So the second row will be the second function with all the variables, and because we have just two functions, we have two rows, two variables, two columns. Yeah. So here goes the functions f1, f2, and here goes the variables x and y. And simply this is this expression, yeah. So this is the f1 with respect to the x, yeah. So that way here we have 2x, this one disappears, no x, and here we have cosine pi x minus derivative of x times cosine to minus sine, and p gets into it, yeah. So just this derivative. Here we are expecting to have derivative also of the first row of our f with respect to y, yeah. Again, nothing, no y, minus 1 as written there, nothing, no y. Yeah? And same for the second row. Here, second function with respect to x. Yeah, so that's why here you have y, no x disappears, and here it manifests in this way. Yeah, derivative of that one with respect to x. Here, derivative of the second row with respect to y. Yeah. X after derivative here, this expression, yeah, I think it's clear, and this disappears. So this is how it's built. Make sense? And you can see that Jacobian is, of course, as well a function of our variables x and y, because it must be, yeah. Like it was with the typically, the same analogy still holds from scalar case to this vector case. And now, having all those sets, yeah, we can write Newton-Raphson's method, yeah, because sometimes it's called that Newton method is for the scalar and Newton-Raphson's is for the vector, yeah. And again, rules are exactly the same, yeah. So we start with some approximation. We have to have initial guess, yeah. So of course we have to guess all those numbers, like here two numbers, uh, and then we use this the same equation. This equation comes from Taylor expansion after cutting the one term, yeah. So this is this approximated solution. And if we change it, we just get this kind of expression that here is our Jacobian matrix. So AX equal to B. We know how to solve it. This is linear sum of equations. You know, there are many methods of this. There is built-in methods, of course, in MATLAB. It starts with it. So delta is difference of those values, yeah. And now we can solve all this easily to get the new approximation. Clear? Any questions? Yeah. So, if step of Newton-Raphson iteration consists of two steps, yeah. So solve the linear system with respect to delta, because we need to write it, because typically when we solve linear system, we need to write it as AX equal to B. Yeah, this is the way how to solve it. And then just, update X. For scalar case, we make it in one step, but here, because we have to divide the matrices, we use this in two steps. We already discussed about this, I believe, if I remember correctly, that linear systems are usually solved using variant of Gaussian elimination. Do you know Gaussian elimination? You can read about this. There is, okay, yeah, yeah. So, well, we are into numerical methods. We won't get into details of solving nonlinear linear equations, because as you can guess, it's topics in themselves, yeah. So it's very common operation. There's the software for handling this kind of equations was developed many years ago, and as you can see, because it goes back to Gaussian, the idea is not so new, yeah. Um, so what is interesting to us, we can efficiently use this implementation using this variant of Gaussian elimination to solve equations, even if the size of equations goes into hundreds, thousands, yeah, because okay, if it goes to millions, sometimes you change the approach, and it's expressed by this operation. I suppose that you know this operation, yeah. And we discuss you should rather use inverse, yeah, because there's really no point for using this, yeah, because it's slower, it's less accurate, so there's not good many reasons to solve it, yeah. Use inverse when you need inverse, and here we don't need inverse. Here is the note that Jacobian is often sparse matrix. Do you know what is sparse matrix? Again, yeah, yeah. So you catch me here, but good that you read, yeah. Okay, yeah, it contains mostly zero elements. Yeah, it matters when you have large systems. But maybe also Alexander mentioned this because it's even more common in finite element method. Have you mentioned? Yeah, no, not really. Yeah, because in finite element, you can get systems that are really huge. Yeah, like really up to millions. Yeah. But even if you write this matrix that is million by million, you can find that you just have 5 million elements instead of, just this million times million. It's quite already big number, yeah? And it's hard to keep it anywhere. But if it's sparse, maybe you just need to keep those 5 million elements that are typically close to diagonal. And there are some special methods, like it's written here, to solve them. But okay.
How the Jacobian matrix is only a function of x already, like because they cannot really decouple it from other matrices. Like it seems that the Jacobian matrix is only a function of one variable. Like we can inverse it, but it is function of x, y, z, for example. I don't understand how this equation is solved.
So, okay, so again, this is just mathematical notation as always, yeah, yeah. So it expresses the fact that we calculate the Jacobian in at point y, I, yeah, because we don't, this is something that we get already, we assume, but if we put xi that we have, this is just a matrix. If we get here, yeah, if we say that x is 0 and y is 1, this is just a matrix that contains, this is 2 by 2 matrix of 4 numbers.
Ignore the other variables.
No, 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 we don't ignore. I don't understand what you mean by ignore. We use, this is numerical methods, yeah? So we, of course, write everything in symbols, but when we get to implementation and usage of it, we put numbers there, yeah? So we use the x vector is, for example, 0, 1, yeah? Because it's 0, 1, so it has some concrete numbers, yeah? If you put the 0, 1 here, because we can evaluate it, we will get some numerical matrix that are 4 numbers here, 2, yeah? Yeah. This will be also numerical matrix. So then we will have the bunch of numbers and we can solve it. Okay, is it clear now? Okay, so it's not written here, but let's take a look on implementation. Newton-Raphson method. Yeah. So it's a little more serious. As you can see, it already contains some description, yeah. But again, it's based on this robust Newton method, yeah. So it takes by analogy f vector function j, our Jacobian matrix, yeah. So this is this partial derivatives x. I think it should be okay. It's not so easy, but x. It should be x0, but this is this initial value and some tolerance. We need still some tolerance. It's iterative method. It will return x, yeah. So our solution and iteration counter in the same way, yeah. And procedure is the same. Calculate value. Here is one difference because we cannot just use ABS because ABS has it's defined well for just scalars. Yeah, so we have to find another thing. This typical thing is one kind of the norm of another. Yeah, we just don't get into details. We get a norm. What is important for us? Norm will be 0 when all elements are 0 and will be positive when any of the elements if is not 0. Yeah. And it has this characteristic that the further away we are from the point 0, 0 on our hyperspace, the larger the norm is. Yeah, so it also means that a very small norm within the tolerance. It means that this value is all the values of this vector are close to 0. Iteration counter for robustification, and again, yeah. So if the norm is larger than tolerance and we are still within our numerical budget, firstly we solve our equation for delta, yeah. So a, b, and x, yeah. This is already a number. We evaluate it here because we just need it once. Then we calculate new value. We update the value of x as it's written here, yeah. So this is the first step, yeah, implemented in that way. Second step, just update of the x, yeah, and then just follow it, yeah. So new value that will be used here and here, new norm to check for here, iteration counter update to get here. I skip here this f for checking for the numbers, it could be also added. And again, if f norm is larger than tolerance, something went wrong, return -1. Make sense? Yeah, so just almost the same, just we have to adjust it that we change from scalars to vectors. But all the steps, almost all the steps are there and are very similar. Uh, so I think I should call it also demo because it doesn't make sense to call it test. Yeah, let's call it demo. Yeah. So demo Newton-Raphson method. So it implements exactly what is here. Yeah. Oh, okay. No, it's test. So it's really a test. So yeah. So let's get back. It should be called test because you can see that there's assert here, so we can use it as a test. But once again, f is our function. Yeah, can you see that this is the same function? X squared. Should I bring it here? Maybe I will bring it here. So here was where I have this example. It's hands-on. We have pretty good timing. So here is our example. Yeah. So let's escape this mode, put it into this mode, and let's put it here. Yeah, okay. So now it's on one screen. So you can see that we have, because the x, we can write it in different way, but here with this kind of compact notation, we know that x is vector. So x contains two elements, x1 and x2. Yeah. So x1 will be referred to x and x2 will refer to y. A little confusing, but I think that, we are good to follow it. So we can see that this is the same function because it's x1 squared minus x2 plus x cosine pi times x. Yeah, first line, first row of our vector, first element of our vector. Second element xy, so x1, x2, yeah, plus axp minus y is second element, so that y is x of 2, minus x to minus 1, exactly, x to minus 1. Next is Jacobian. Uh, so Jacobian is matrix, yeah, 2 by 2, but it's exactly the same. 2x1 plus cosine pi x1 minus pi x1 sine pi x1 x. Yeah, so exactly the same. Minus 1 plus minus 1. Here it's y, so x2 plus x minus 2 minus 2 to power minus 2. And here is x minus exponential of minus y. Yeah, the same. So from different sources, we know that we expect to get 1, 0 as a solution, and we can even check that it works. Yeah. So if we put here 1, so this is 1, 0, this is 1, and this is cosine of pi is also 1. Yeah. So 1 minus 1 works, is 0. Yeah. And here this is 0, this is 1, this is minus 1, works as well. Yeah. So we use tolerance, Newton-Raphson method, some initial guess like 2 minus 1, something that we have to choose, tolerance, and we check if expected is close enough. ABS will return a vector as well because it's meant for scalar, so we get the, for example, norm of the error that it's small enough. Yeah. I think this ABS is not even needed here. The result will be the same, but okay. So let's run it. And as with correct test that it was passed, nothing has happened. Yeah. So we can just clear the stuff. Uh, and see, run it again. And you can see that the error, so it's pretty low, yeah, as required by tolerance, that we get solution in 4 steps, and that the actual solution that was produced is 1 and 10 to minus 6, because tolerance was 10 to minus 4, so it's below tolerance, clearly. Okay, so it works. Any questions? Does it need any kind of, more closer presentation, or it's something that surprises you? Or yeah. So I think that the analogy between scalar case and this vector case is clear. Yeah. Algorithm is the same. Sorry, if we take a look on Newton-Raphson method and Newton's method, uh, you can see that it's very similar, just slightly different names, but we calculate the value. Instead of ABS, we need norm, but I think this is clear why. Then this is much simpler because on the scalar, but here those 2 steps do exactly the same. X is updated with delta, so this is delta here, so we could write it in exactly the same way, yeah. And the rest is similar, yeah. So what I have left only for today is the introduction to our kinematical analysis of mechanical systems. Yeah. So here you can see already mechanical system. It's pretty easy, so you can calculate it using some geometrical principles. But okay, so there is something good. But we don't really want to do this simply because we aim for computer aided system. In general, first of all, it takes time to calculate it. We want to have the system that works for multiple different mechanism in similar way. So that's why we can just define the mechanism and solve it. Also, kinematic analysis, it means that we are interested, for example, in time evolution of the system. Yeah. So while here we are asked what are some values for this mechanism with respect to something else, typically we would assume that it moves somehow. Yeah. So we also want to know what is the time history for it. Yeah. So there's many ways to solve it numerically. Yeah. So I think that I hope that this plot is self-explanatory. Yeah, that we have here just this link that is connected at point A to ground. Yeah, and this link is connected with this round object. Yeah, maybe some circle, whatever. Yeah, some disk, and it's misplaced with respect to center of rotation by A. Yeah, and this disk has radius r, yeah, and those values are put it here. So a is this distance between our 2 points, r its radius, and b is length of this link, yeah. And we assume that this angle is given, like it's 30 degrees, yeah, and the question is, what is the distance between point A and the center of this disk, and what is the angle here between between this horizontal line and this part. So in practice, this is the angle of this disk. Is it clear? What is the task? So how to solve it using Newton-Raphson? We need to write some equations that express the structure of this mechanism. Yeah. So we know that we need to write how many equations? Yeah, exactly. Because we want to find two values, so we need two equations. Yeah. And we need to write this equation in the form that something is equal to zero. Yeah, to solve it using Newton-Raphson. This is one thing that we know. And another that, of course, this must depend on those variables. Yeah. So what we can do here? An idea? Do you know this kind of the problems? Here we can write so-called loop equation. Yeah. So this loop equation, it means that we will write vector equations based on the vectors that we can draw inside of this system. Yeah. And it's loop equation because it's equal to zero. Yeah. So in our case, can I draw here someone? Okay, I have to check it. In our case, our loop equation would be, for sure, I should be able to draw somehow here. Okay, just give me a second. I will turn off this mode, get draw. Okay, here is some kind of pencil. It's nice, yeah. So we can see already here a solution, but yeah. To explain it, so loop equation would go like that, that here we have one vector, yeah, along this link B. Here we have another vector along this line from this point of attachment to the center of this disk, yeah. This is another vector. Just from this point to the point where it touches the ground, yeah. And the final vector is here. Okay, so maybe my drawing, especially using this device, it's not the prettiest, but I hope that you get the idea, yeah. So first of all, it's loop equation because it's closed equation, so it gets up to zero, yeah, because it's based on the it's always valid because of the how the mechanism looks at work, yeah. It also includes all the kinematic properties that we have, yeah, because it must tell us about, must include those angles, those displacements, and other stuff, yeah. So that's why we can write it in that way. You can check it, or we can write it later because today we are running out of time already, a little over the time. But as you can see, uh, here is the version of this loop equation, yeah. And as you can see, what is nice, it either contains the values that are known, like B, R, and A, and it contains the other values, yeah, that one is given, like phi1, but it contains phi2 and D. So because of this, we can solve it, yeah. And this is pretty simple, so we can check that this is simply correct, yeah. We can address it the next time if you have any doubts. But of course, we can also calculate the Jacobian matrix based on this with respect to U, because U is simply phi2 and D. So this is just to give you a brief introduction into kinematical system, into mechanical systems, and how kinematic analysis can be done in the way using those algorithmic approaches. And yeah, we'll work in the future also about the methods how to make it even more automatic. Yeah, because now this as you can see, this loop equation depends on the topology. So if you want to write this kind of loop equation for general systems that are possibly very complicated, yeah, like a car suspension or something like that, then we need to make topology analysis. It can be done, but it's not super trivial, but there are methods to address all this. But I hope that it gives you just a glimpse of what we are aiming at. You can think about this example. We'll for sure get back to it. And if you have no further questions, yeah, this is all from my side for today. Of course, yeah, yeah, it isn't. Yeah. That's why you have to be very close, because, for example, even for this system, yeah. So let me use different color. Uh, yeah, because even for this system, I believe that you could have A here, this point here, and link here. Yeah, and it will be in, and it will be, it could be correct, yeah, like here, the solution. Maybe not for this x1, but it gives you example that you can have very, very similar configuration and some parts are still the same. Or because here, rather for this angle, this disk could be on the other side, yeah. So maybe I can correct it. Can I just take it back, yeah? That for the same system, yeah, you could have, could you have this it here? Okay, maybe I have to think about this. Yeah, because D is our variable and angle is our variable. So in theory, we could have, like it here, yeah, as well. Yeah, so if we have disk here, so if this is instead of being here, would be here, it would still give you the same the same set of equations, yeah, because equations are independent on this configuration, and it's another valid solution. This also means that we want to get those values approximately well. Yeah, so yeah. And we can check that if you get those values from this more like the second system, that we just get another solution that it's still valid. So yeah, yeah, very valid comment. Anything else? So any suggestions to anything about this course as well? Ideas how to improve it? Okay, no problem. Yeah, if not, yeah, so thank you very much for your attention, and yeah, we will meet hopefully in 2 weeks. Yeah, thank you.